In this video, we'll explore what this vast cosmic void truly is, how it was discovered, and what it means to live inside it. A revelation that could force us to rethink everything we know about the universe itself. The universe around us is not what it seems. For decades, astronomers believed that if you zoomed out far enough, everything would even out. That matter, galaxies and clusters would blend into a smooth cosmic average. But in 2013, a team of scientists discovered something that changed that idea completely. They found that our region of space is missing matter, a lot of it. We live inside a gigantic, underdense bubble nearly 2 billion light-years wide, where galaxies are about 20% scarcer than the cosmic average. It's called the KBC Void, named after the astronomers who mapped it, Ryan Keenan, Amy Barger, and Lennox Cowie. And it's not just another feature of the universe, it surrounds us. Everything we see, every measurement we make, passes through this cosmic hole before it reaches our telescopes. The discovery began with a simple question: how evenly are galaxies spread through space? To find out, astronomers mapped tens of thousands of galaxies in every direction, plotting not only where they appeared on the sky, but how far away they were. When those distances were added, a strange pattern emerged. Close to home, the number of galaxies dropped. Not slightly, significantly. The pattern held no matter which way they looked. Our cosmic neighbourhood was thinner than it should be. This was not a small gap between clusters. It was a region hundreds of millions of light-years across where the density of matter fell steadily toward our position. We were not at the edge looking in. We were sitting in the middle of it. At first, that conclusion sounded impossible. According to the standard model of cosmology, the framework known as lambda cold dark matter, the universe should look roughly uniform when averaged over large enough distances. There should be voids, yes, but nothing this enormous or this empty. To produce such a structure by random chance would be extraordinarily unlikely, yet the data would not go away. The KBC team cross-checked galaxy catalogues, compared independent surveys, and recalculated distances using multiple methods. The result was always the same. The density of galaxies within roughly 1 billion light-years of the Milky Way was lower than the cosmic average, and that low density extended outward in every direction. The implications were immediate. If our region of space is underdense, then the expansion of the universe might appear faster here than it really is. That simple fact could explain one of the biggest mysteries in modern cosmology, the Hubble tension, the long-standing disagreement between local measurements of the universe's expansion rate and those based on the ancient light of the cosmic microwave background. Inside a void, there is less gravity pulling matter together, so space can expand slightly faster. From our vantage point within the KBC void, galaxies would seem to be moving away from us more quickly than the cosmic average. What appears to be a faster expanding universe might actually be the result of our unusual location. We're not measuring the entire cosmos, we're measuring it from inside a cosmic dip. But that answer came with a cost. If true, it challenges a principle that has guided cosmology for a century, the cosmological principle, which states that the universe is homogeneous and isotropic, essentially the same everywhere and in every direction. Living inside a giant underdense region would make our location special, a violation of that assumption. For many scientists, that was difficult to accept. The debate intensified as new observations arrived. Surveys of galaxy motion showed that galaxies near the edges of our local region were drifting outward, as if pulled by denser structures beyond the void's boundaries. The velocities matched predictions for a slowly expanding underdensity. Other researchers confirmed that the cosmic microwave background light, when passing through these vast empty regions, shows subtle temperature dips, a signal of lower gravitational influence. Piece by piece, the evidence built a consistent picture. We are surrounded by a vast, gentle hollow in the cosmic web. Skeptics looked for alternative explanations. Perhaps the surveys missed faint galaxies hidden by dust. Perhaps local gravitational flows or nearby superclusters were distorting the counts. But repeated analyses with independent data produced the same underdensity. The void remained. And so, a once fringe idea began to move toward the centre of discussion. The KBC Void might not only exist, it might be reshaping our view of the universe. If we truly inhabit such an environment, then every cosmological constant, every distance estimate, and every model built from local observations could carry a subtle bias. We might have to correct for where we are before we can understand what we see. The void also forced scientists to rethink cosmic structure formation. In the early universe, small differences in density, tiny quantum ripples from the first moments after the Big Bang, grew under gravity's pull into the clusters, filaments, and voids we observe today. But simulations rarely produce voids this large or deep. Something about our initial conditions, or about how gravity and dark energy interact on the larger scales, might need to change to make such a structure possible. If the void is genuine, it could signal missing physics, perhaps a variation in dark energy's behaviour over time, or a subtle modification of gravity itself, or it could simply be the improbable outcome of cosmic chance. Either way, it reminds us that we do not observe the universe from nowhere. We observe it from one particular location, shaped by the environment around it. Over time, the numbers have sharpened. The underdensity is about 20% below average. The void's radius, roughly 1 billion light-years. The Milky Way sits not exactly at its centre, but comfortably inside it, nestled within the Laniakea supercluster, one of the rare concentrations of matter floating in an otherwise sparse region. Beyond the void's edge, galaxy density rises again, linking to the denser filaments and walls that form the framework of the cosmic web. What makes this discovery extraordinary is that it touches everything we measure. Every photon from the distant universe crosses this underdense space before reaching us. Every redshift, every supernova, every signal of cosmic expansion is filtered through the environment of the KBC Void. Understanding it is not optional. It's essential if we want to know what the universe is really doing. The discovery of the void doesn't mean the universe is broken. It means our picture of it is incomplete. Cosmology has always advanced through better maps, better ways of understanding where we are in relation to everything else. The KBC Void is a new kind of map, one drawn not from what we see, but from what we don't. It tells us that emptiness is not absence. It has structure, influence, and history. Perhaps that's the greatest irony of all. To understand the universe, we must first understand the nothing that surrounds us. The KBC Void may sound like a region defined by absence, but emptiness itself has power. In fact, the vast hollows between galaxies are where the universe reveals one of its greatest mysteries. Inside them, dark energy reigns. In dense regions, clusters and filaments, gravity holds sway. There, matter clumps together, resisting the pull of cosmic expansion. Galaxies tug on one another, merging and colliding, forming new stars from the wreckage. But in the deep stillness of a cosmic void, gravity loses its grip. There are no massive clusters to anchor the surrounding space, no dense walls of matter to slow the expansion. Instead, dark energy takes full control, pushing everything apart faster than anywhere else in the cosmos. That difference makes voids the best natural laboratories for studying dark energy. They are the only regions where its effects act freely, unopposed by matter. In a sense, a void is dark energy made visible, space itself, stretching under its own mysterious force. Dark energy is unlike anything else in the universe. It does not clump or flow. It does not emit light or interact with matter directly. It is simply there, woven into the very fabric of space, exerting a uniform negative pressure that accelerates expansion. It was discovered in 1998 when distant supernovae appeared dimmer than expected, evidence that the universe's expansion is speeding up, not slowing down. Today, scientists estimate that dark energy makes up about 68% of the total energy of the universe. Ordinary matter, everything we can see, touch and detect, accounts for less than 5%. The rest is dark matter and dark energy, unseen but fundamental. Together they govern how the cosmos grows and evolves. In clusters of galaxies, gravity counteracts dark energy's push, keeping the galaxies bound. But inside a void, there's almost nothing to fight back. The result is a faster local expansion. Galaxies near the centre drift apart slightly quicker than those at the edges. Over billions of years, the void grows larger and emptier. The process is self-reinforcing. As matter drains away, gravity weakens further, and dark energy's influence increases. The emptiness expands itself. This makes voids perfect places to test whether dark energy behaves as a constant, unchanging force, or as something more complex, a dynamic field that varies over time and space. If dark energy is constant, voids should expand uniformly, maintaining roughly spherical shapes as they grow. If it fluctuates, the expansion could differ in strength or direction, leaving subtle distortions in the shapes of voids across the universe. Astronomers are now measuring these shapes with increasing precision. So far, most large voids appear roughly round, consistent with a uniform dark energy field. But the measurements are still young, and the data could yet reveal small variations. Even slight asymmetries, voids stretched more in one direction, might hint that dark energy is not the same everywhere, or that gravity itself changes at cosmic scales. The growth history of voids is like a record of dark energy's behaviour through time. From the first few billion years after the Big Bang, voids began forming as matter flowed away from slightly underdense regions. Those tiny early differences have been magnified over cosmic history. By comparing voids of different sizes and distances, astronomers can trace how fast they've grown, and in doing so, reconstruct how the universe's expansion rate has changed. If dark energy were weaker in the past, voids would have expanded slowly at first, and then sped up more recently. If it's truly constant, the growth rate would show a smooth, predictable acceleration. Early results lean toward constancy, but the evidence is not final. The next generation of telescopes like the Vera Rubin Observatory and the Euclid Space Telescope will map thousands of voids with far greater detail, turning these vast regions into precise measuring tools for cosmic acceleration. One of the most promising ways to probe dark energy through voids is by studying their edges. The boundary of a void is not a sharp wall, but a gradual rise in density, a transition zone where sparse matter inside meets the filaments outside. Over time, that boundary moves outward as material drains from the void's interior into the surrounding web. The speed and shape of that movement depend directly on how dark energy acts. If expansion is accelerating faster, the boundary retreats more quickly. If dark energy is weaker, the boundary slows. By comparing the current positions of void edges to computer simulations of cosmic evolution, scientists can infer how strongly dark energy has pushed over billions of years. Early measurements suggest that dark energy has remained roughly constant for at least the last 6 billion years. But small deviations are still possible, hidden within the uncertainty of current data. Every new survey brings the chance of a surprise, a subtle shift that could signal that dark energy is not a static property of space, but something that evolves. What's remarkable is how clearly voids isolate these effects. In clusters and filaments, gravity, gas, and feedback from galaxies all interfere with expansion measurements. But in a void, those complications fade. There is little matter to confuse the signal, no intense gravity to warp the flow of space. The few galaxies that inhabit a void move almost entirely due to cosmic expansion itself, not local interactions. For cosmologists, that simplicity is gold. It allows them to separate the universe's large-scale behavior from the messy details of individual galaxies. Inside a void, a single galaxy drifts through darkness almost alone. There are no nearby neighbours tugging at it, no dense clusters lighting the sky. Yet even here, there is structure. Galaxies within voids tend to be small, gas-rich, and blue. Their stars forming slowly but steadily. They live quiet lives compared to their cousins in crowded regions. The low-density environment means few collisions or mergers, processes that in denser parts of the universe trigger starbursts and black hole-feeding frenzies. Void galaxies evolve in peace. They hold on to their gas longer, unstripped by encounters or cluster winds. Occasionally, internal instabilities ignite bursts of star formation, consuming the stored gas in short-lived flares before fading back into stillness. Over billions of years, these galaxies remain modest and undisturbed, preserving a glimpse of what early galaxies might have looked like before the universe grew crowded. Their existence proves that even in near emptiness, the cosmos never truly stops forming structure. Gravity, though weakened, still gathers enough matter to create islands of light in the darkness, but the void sets a limit. Below a certain threshold, about 35 kilometers per second of circular velocity, a dark matter halo cannot hold on to gas. The gravitational pull is too weak. The gas escapes into intergalactic space. These invisible halos populate the void too, silent and starless, filled with dark matter but devoid of light. They are galaxies that never quite became galaxies at all. This filtering effect defines the ecology of voids. Only the most resilient structures can exist there, small but self-contained, slowly evolving without outside interference. It's an environment stripped down to the essentials: gravity, expansion, and time, and in that simplicity lies clarity. The fewer variables, the easier it becomes to see which cosmic forces truly matter. That's why cosmologists are fascinated by the KBC Void in particular. Its size and proximity make it the perfect testbed for the universe's most elusive component. Because it surrounds us, we can study it in unprecedented detail. Every galaxy survey, every supernova measurement, every baryon acoustic oscillation study passes through it. The void is both the problem and the tool. It might distort our measurements, but it also gives us a unique way to study the distortion itself, to understand dark energy not as an abstraction, but as an active force shaping the space we live in. The irony is striking. For centuries, emptiness was considered nothing more than the absence of matter, a blank backdrop to the true stage of the universe. But today, we know that the opposite is true. Emptiness is where the most fundamental physics plays out. Voids are where the laws of the cosmos reveal themselves most purely. Inside them, the universe's hidden energy becomes visible, not through light, but through motion, the slow, steady stretching of space. The KBC Void turns that realization into something personal. We're not outside observers looking into the void. We're inside it, participants in its expansion. Our measurements of cosmic acceleration, our estimates of the universe's age, and even our understanding of its fate are all filtered through this vast region of nearly nothing. The emptiness defines what we see. As the universe continues to expand, voids like ours will grow even larger. Matter will drift farther toward the filaments, and the gaps between them will widen. Eventually, voids will dominate the cosmos completely. The universe will become a landscape of isolation, small islands of galaxies separated by immense oceans of dark energy. In that distant future, the last remnants of structure will float through expanding emptiness, each one a tiny witness to a universe still accelerating into the dark. For now, though, we live in a rare and precious moment when both structure and emptiness coexist, when galaxies still form and the cosmic web is still visible. The KBC Void is not just a curiosity of cosmic geography. It's a reminder that even in the most desolate corners of the universe, the forces shaping everything remain at work. We live not just in a galaxy, not just in a supercluster, but in a vast and expanding cavity of space, a place where gravity fades and dark energy takes command, a place where the universe reveals what happens when matter steps aside, and nothing is left but the pure expansion of space itself. Inside the void, the universe is writing its future, slowly, silently, and in the language of emptiness. When astronomers first began mapping galaxies in 3 dimensions, they expected to see a random scatter of points, an even sprinkling of light across the darkness. What they found instead was one of the most intricate patterns in nature. Galaxies were not scattered at all. They were arranged in long, interconnected filaments, woven together into an immense cosmic web stretching across the observable universe. Between those glowing threads lay vast empty regions, voids hundreds of millions of light-years wide. The web looked almost biological, like neurons in a brain or the filaments of a living cell. The similarity was not coincidence. It was the natural result of physics playing out on the grandest possible scale. This is the true structure of the cosmos. Clusters of galaxies form at the intersections of filaments. Filaments connect into sheets. Sheets surround immense cavities of near emptiness. Together, these structures define the texture of the universe, the pattern imprinted by gravity acting on tiny irregularities left over from the Big Bang. The cosmic web began as sound. In the first few 100,000 years after the universe's birth, space was filled with a dense hot plasma of particles and light. Tiny variations in density created pressure waves, acoustic oscillations that rippled outward, compressing and rarefying matter. When the universe cooled enough for atoms to form, those ripples froze in place. The result was a subtle pattern. Regions slightly denser or emptier than average, spread across the young cosmos. Over billions of years, gravity magnified those tiny differences. Dense regions pulled in more matter, growing into filaments and clusters. The underdense regions expanded faster, draining matter away and becoming voids. The cosmic web is the frozen echo of those ancient sound waves, evolved through time into a vast 3-dimensional network. Modern surveys have revealed its structure in extraordinary detail. The Sloan Digital Sky Survey, one of the most ambitious mapping projects ever undertaken, measured the positions of millions of galaxies. When plotted in space, those data points form a breathtaking picture. Filaments hundreds of millions of light-years long, arching and twisting through cosmic emptiness. Between them lie great voids, the dark spaces that make up most of the universe's volume. One of the most striking features revealed by these maps is that the Milky Way and its neighbouring galaxies are part of a much larger structure, the Laniakea supercluster. It spans over 500 million light-years and contains around 100,000 galaxies. All of them are moving along the filaments, drawn by gravity toward a common centre of attraction known as the Great Attractor. This motion defines Laniakea's boundaries. Everything flowing toward that gravitational basin belongs to the same supercluster. But here lies a paradox. Laniakea, immense as it is, sits entirely within the KBC Void. It is a massive island of matter floating in a cosmic sea of emptiness. On the larger scales, the void dominates. On smaller scales, filaments and superclusters persist, tracing out delicate patterns even within the underdense environment. The contradiction is only apparent. Density in cosmology is a matter of scale. The void is underdense when averaged over billions of light years, but that doesn't mean it is empty. Within it, smaller clumps of structure still exist, filaments connecting galaxies, groups forming clusters, and stars forming within those galaxies. The void is a landscape of contrasts, an intricate fractal pattern where emptiness and structure coexist at every level. To visualize it, imagine the universe as a sponge. The solid filaments and clusters form the thin, interconnected framework, while the bubbles are the voids. Most of the volume is empty, but the matter is concentrated in the delicate walls between cavities. The KBC Void is one of those bubbles, an enormous hollow in the cosmic sponge, with Laniakea as a denser patch on its surface. The cosmic web is not static. Galaxies and dark matter continuously flow through it, moving along filaments like rivers draining toward gravitational valleys. Over time, the dense regions grow denser as matter accumulates, while voids expand and empty out. This process of gravitational clustering is the engine of cosmic evolution. It is slow, taking billions of years, but relentless. The flow of galaxies within and around Laniakea shows this beautifully. Those near the Great Attractor fall toward it faster. Those near the edges of the supercluster move more slowly, even beginning to drift outward under the influence of the surrounding void. Beyond Laniakea, the pull of an even larger structure, the Shapley supercluster, about 650 million light-years away, extends its reach, drawing entire regions of the cosmic web toward it. These interconnected flows reveal the hierarchy of the universe. Galaxies orbit within clusters. Clusters stream along filaments towards superclusters. Superclusters themselves fall toward even larger overdensities, pulled by gravity across hundreds of millions of light years. The cosmic web is dynamic, a living system of motion and balance, shaped by the competing forces of gravity and cosmic expansion. Yet even this grand structure is temporary. As dark energy accelerates expansion, gravity's influence weakens over long distances. The filaments will gradually thin, and the flows that bind superclusters together will slow. Eventually, only the most tightly bound regions, clusters, and local groups will remain gravitationally connected. The cosmic web we see today is a snapshot in time, caught between its youthful growth and its eventual dissolution. Still, while it lasts, it offers a map of cosmic history written in geometry. The distances between filaments, the sizes of voids, and the distribution of clusters all encode information about the universe's past expansion rate and the strength of its gravitational laws. The web is a fossil record of cosmological evolution, frozen evidence of how matter responded to the forces that shaped it. One of the key tools used to study this structure is the baryon acoustic oscillation scale, a relic of those early sound waves. The characteristic distance those waves travelled before freezing, about 490 million light-years, appears as a preferred spacing between galaxy clusters. By measuring that spacing at different epochs, astronomers can determine how the universe's expansion has changed over time. It's an elegant method. The universe carries its own ruler, built from the sound of its birth. When scientists apply this ruler to nearby galaxies, the results match the expected pattern. But within our local region, the scale appears slightly stretched. This is exactly what we would expect if the KBC Void is real. The underdense environment expands faster, stretching the cosmic ruler in our vicinity. The baryon acoustic oscillation signal provides independent confirmation that our part of the universe is expanding differently from the cosmic average. The same large-scale maps that reveal the cosmic web also show how rare such immense voids are. Most empty regions are a few hundred million light-years across. The KBC Void, nearly 2 billion, stands out as an anomaly, one of the largest coherent underdensities ever measured. In a universe governed purely by random fluctuations, such a region would be improbable. Its existence hints that our models might be missing something about how structure forms and evolves on the larger scales. Perhaps the initial conditions of the universe were slightly different than we think. Maybe certain regions started out less dense, setting the stage for larger voids to form. Or perhaps gravity itself behaves differently over vast distances, altering how quickly matter collapses and empties. Whatever the cause, the KBC Void shows that the cosmic web is still full of surprises. As astronomers look deeper, they find even greater patterns. Superclusters and voids connect into supervoid complexes, spanning billions of light-years. The largest known, the Eridanus supervoid, is comparable in size to the KBC Void and may even be connected to it through faint bridges of low-density space. These vast structures raise profound questions. How far does the web extend? Are there larger patterns beyond the observable horizon? Could our entire region of the universe be just one cell in a still greater cosmic structure? For now, we can only observe what light has had time to reach us. Beyond that limit, 13.8 billion light-years away, the web fades into the afterglow of the Big Bang. But even within our visible universe, the scale and complexity are staggering. Hundreds of billions of galaxies, each containing hundreds of billions of stars, arranged in filaments spanning unimaginable distances, all connected by the invisible gravity of dark matter. When we step back far enough, the universe stops looking like a random scatter of galaxies and starts looking like something designed. A vast, self-organizing network shaped by simple physical laws. Yet this apparent order arises naturally, without any guiding hand. It's the emergent geometry of matter responding to gravity, dark energy, and time. The cosmic web teaches a humbling lesson. We tend to imagine ourselves as isolated, living in a galaxy drifting through empty space. But in reality, everything is connected. The Milky Way is part of a filament, that filament part of Laniakea, and Laniakea itself just one ripple on the surface of an immense cosmic sea. Even the void surrounding us is not separate from the web. It is part of its structure, defined by the same forces that created everything else. If we could see the universe all at once, we would not see a simple collection of galaxies. We would see a luminous network stretching in every direction, a web of matter and emptiness spanning all of space, evolving over billions of years. And within that network, we would see our position, a small, quiet galaxy in a modest filament, floating inside a vast underdensity on the edge of an immeasurable structure. The cosmic web is the framework of existence. It connects every galaxy, every cluster, every void into a single system. It is the skeleton of the universe, the invisible architecture that gives shape to everything we see. And within its grand design, we're a single thread of light, living, observing, and trying to understand the web that made us. One of the most important numbers in science is how fast the universe is expanding. It's called the Hubble constant, a measure of how quickly galaxies move away from each other with distance. For nearly a century, astronomers have tried to pin down its exact value. The answer defines the universe's age, its size, and its fate. But the deeper we look, the stranger that answer becomes. Today, there are two main ways to measure the Hubble constant, and they don't agree. The first comes from the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. Using satellites like Planck, scientists can model the universe's entire history, tracing its expansion from the first moments to today. That method gives a value of about 67 kilometers per second per megaparsec. The second method looks at the local universe, supernova, galaxies, and variable stars relatively nearby, and measures how fast they're receding. That gives a higher value, around 73 kilometers per second per megaparsec. The difference might sound small, but in cosmology it's enormous. It's the difference between a universe that's 13.8 billion years old and one closer to 12.7, between models that work perfectly and models that fall apart. And despite years of testing, improved data, and countless cross-checks, the gap refuses to close. This disagreement is known as the Hubble tension, and it has become one of the biggest mysteries in modern physics. It's a problem so fundamental that resolving it could lead to new discoveries about dark energy, dark matter, or even the laws of gravity themselves. But what if the answer isn't hidden in the early universe, or in new physics at all? What if it's here, around us? If we live inside a vast underdense region, a cosmic void like the KBC Void, then the space around us is expanding faster than the cosmic average, and that could explain why local measurements of the Hubble constant are higher. Here's how it works. In dense regions of the universe, gravity slows expansion. Matter pulls on itself, resisting the stretch of space, but in a void where matter is scarce, gravity's pull is weaker. Space is free to expand more rapidly. That means galaxies inside or near a void will appear to move away faster than those in denser environments. So if astronomers are measuring galaxies and supernovae inside our local void, they'll see a higher expansion rate. But when scientists use the cosmic microwave background to calculate the global expansion rate, they're measuring the universe on much larger scales, beyond the void, where the expansion is slower. The result is two perfectly accurate measurements that disagree because they're taken from two different regions of the universe. The so-called Hubble tension might not be a conflict at all. It might simply be a perspective effect. Ryan Keenan and his colleagues proposed this idea in 2013, and since then, other teams have tested it. They simulated universes with large underdense regions similar to the KBC Void and measured the apparent expansion rate from inside. The results were remarkable. Observers within such a void would measure a local Hubble constant higher by about 5 to 7%, almost exactly the observed discrepancy. This doesn't mean the tension is fully resolved, but it shows that the void hypothesis can reproduce the difference naturally, without invoking exotic new physics. It's a humbling idea. We might be overestimating the universe's expansion rate simply because of where we happen to live. Still, not everyone is convinced. Critics point out that to produce the observed tension, the void must be both large and deep, perhaps too large to form naturally in the standard model of cosmology. Simulations based on the lambda CDM framework, lambda cold dark matter, rarely produce voids spanning billions of light years with a 20% underdensity. The odds of such a structure forming by chance are extremely small. If the KBC Void is real, it might imply that our cosmological models underestimate how large fluctuations can grow, or that the initial density variations in the early universe were slightly stronger than we think. Alternatively, it could mean that the way gravity behaves on the larger scales isn't exactly what general relativity predicts. Each possibility is extraordinary and unsettling. To test the void explanation, astronomers look for its predicted signatures. One key test is the integrated Sachs-Wolf effect, a subtle distortion in the cosmic microwave background caused by light travelling through changing gravitational potentials. As CMB photons pass through an underdense region like a void, they lose a little energy entering it and gain slightly less when exiting, because the void expands while they travel. The result is a faint cold spot in the CMB map, a temperature dip aligned with the void's location. Observations have indeed found such cold spots correlated with known supervoids, including one in the constellation Eridanus that may be related to the KBC Void. The effect is small, millionths of a degree, but detectable. Each new detection strengthens the case that voids are not only real, but also influence how we see the universe's oldest light. Another line of evidence comes from the peculiar velocities of galaxies, their motions beyond the general expansion of the universe. In and around a void, galaxies tend to flow outward, away from the low-density centre, moving toward denser regions at the edges. If we live inside a void, our entire local group of galaxies would be part of that outflow. Observations show precisely that. A large-scale flow of galaxies stretching hundreds of millions of light-years, consistent with the direction and amplitude predicted by a local underdensity. Together, these clues form a coherent picture. The underdense environment of the KBC Void naturally produces a higher local expansion rate, outward galaxy flows, and slight distortions in the CMB, all of which we observe. It doesn't require new particles or exotic forces, just the recognition that our cosmic neighbourhood might not be average. Yet even if the void explains the Hubble tension, it introduces new puzzles. The cosmological principle, the assumption that the universe is homogeneous on large scales, is a cornerstone of modern cosmology. It's what allows us to treat the universe as a single, smooth system, and describe it with a few global parameters. If we live in a rare underdense region, that assumption weakens. The universe might still be homogeneous overall, but our position within it becomes special. We would be observers inside a bubble, measuring the cosmos through the lens of our local environment. That idea makes many cosmologists uneasy. It evokes older models of the universe where humans occupied a privileged location, something modern science has long tried to move away from. But the principle of mediocrity, that we live in a typical place, is not a law of nature. It's an assumption, and assumptions are only as good as the evidence supporting them. The KBC Void forces us to question that evidence. Suppose the void explanation is correct. What would that mean for the age of the universe? If local expansion is faster, then distances to nearby galaxies are slightly overestimated. Correcting for that would lower the locally measured Hubble constant, bringing it closer to the value inferred from the CMB. The global age of the universe, about 13.8 billion years, would remain the same, but our local measurements would appear to suggest a younger universe, around 12.7 billion years. Interestingly, independent methods of estimating stellar ages, like dating ancient globular clusters and white dwarfs, consistently yield ages near 13 billion years, matching the older value. That agreement hints that the slower, global expansion rate may be the true one, while the faster local rate is an illusion caused by our position in an underdense region. In this view, the Hubble tension isn't a problem to be solved, it's a perspective to be corrected. But science advances through skepticism, and the void hypothesis must withstand every test. Some astronomers argue that the void alone cannot account for the full difference in expansion rates. Others point out that even if we live in an underdense region, its effect might be too small to explain the entire tension. Still, when combined with other local effects, like the gravitational influence of nearby structures, the void could contribute significantly. The debate continues, but the implications reach beyond numbers. The Hubble tension reminds us that measuring the universe is not just about instruments and data, it's about where and when we measure. Our perspective matters. Every observation is shaped by our position in the cosmic web, by the flows of matter and light through the structures surrounding us. If we're inside a vast cosmic void, we're not at the centre of the universe, but we might be at the centre of a unique and delicate illusion, one that makes the universe appear to expand faster than it truly does. In a way, that realization fits a deeper pattern in the history of science. Again and again, we've learned that our view of the cosmos is biased by our location. Once, we thought Earth was the centre of everything. Later, we discovered the Sun was just one star among billions, our galaxy just one among trillions. Now, perhaps, we're learning that even the cosmic environment we inhabit is not representative, that we live in a rare pocket of emptiness, quietly distorting our perception of the whole. The KBC Void turns the Hubble tension from a problem into a message. It tells us that understanding the universe requires more than measuring its expansion. It requires understanding the space through which we observe that expansion. The universe may be vast, but our perspective is always local. We measure infinity from inside a bubble, and that bubble, the void we live in, may hold the key to reconciling two of the most precise yet conflicting measurements in all of science. If the void hypothesis proves true, it would not just resolve a cosmic discrepancy. It would reveal that our place in the universe subtly shapes the way the universe appears. The cosmos would be the same everywhere, yet our part of it, our cosmic neighbourhood, would bend our perception of time, distance and motion. We would finally understand that the Hubble tension was not a sign that the universe is inconsistent, but a sign that it is vast enough for perspective itself to matter. And that realization, quietly and profoundly, would remind us of something simple. Even in the emptiest places, the universe is never truly uniform. Where we stand shapes what we see. Gravity has always been our guide to understanding the universe. It sculpts galaxies, forms stars, and binds planets to suns. It gives structure to everything. From Newton's falling apple to Einstein's warping of space-time, gravity has always pulled inward, toward mass, toward center, toward everything that exists. But what happens when there is almost nothing left to pull on? Inside a cosmic void, gravity behaves in a way that seems at first impossible. Instead of pulling inward, it pushes outward. Not because gravity itself has changed, it hasn't, but because of geometry and imbalance. In a void, nearly all the matter lies outside, in the dense walls and filaments that surround the emptiness. Those walls exert gravitational attraction, pulling galaxies inside the void outward toward their denser boundaries. The result is a slow, steady evacuation, a cosmic outflow where galaxies drift away from the center, not toward it. In other words, voids don't collapse, they expand. They are, in a sense, gravity turned inside out. To visualize it, imagine standing in a valley surrounded by mountains. Gravity always pulls you toward the mountains, which means away from the center of the valley. Inside a void, galaxies experience the same effect, except the landscape is made of space-time itself. The mountains are the dense regions beyond the void's edge, the filaments, walls, and clusters. The valley is the emptiness between them. Gravity from all that exterior matter pulls galaxies outward, creating a net flow away from the void's heart. This flow is not just theory, it's observable. Astronomers can measure it by mapping peculiar velocities, motions of galaxies relative to the smooth cosmic expansion. Normally, galaxies recede from one another because the universe itself is expanding, like raisins in rising dough. But superimposed on that motion are local flows, caused by gravitational differences between regions of varying density. By studying those flows, scientists can detect the presence of voids, even when they can't see them directly. Galaxies near the centers of voids move outward faster than cosmic expansion alone predicts. The farther they are from the center, the slower that extra motion becomes until it reverses direction near the dense walls beyond the void's boundary. The pattern forms a kind of gravitational fingerprint, a telltale sign of emptiness. When astronomers mapped this pattern around our own region of space, they found something remarkable. The Milky Way is moving at roughly 600,000 miles per hour away from a nearby underdense region called the local void, and that motion lines up perfectly with the direction of the larger KBC Void beyond it. Our galaxy, it turns out, is part of a grand evacuation, one that has been unfolding for billions of years. This outward motion is subtle on human timescales, but dramatic on cosmic ones. Every million years, the Milky Way drifts another 160 million kilometers through space, carried along by the combined gravitational push of surrounding structures. The flow is continuous, relentless, and vast. It's not just our galaxy that moves this way. The entire local group, including Andromeda and dozens of smaller galaxies, is sliding together away from the local void center and toward the Virgo cluster, a dense concentration of matter about 60 million light-years away. Virgo's gravity acts as a distant anchor, pulling everything nearby toward it. Between the pull of Virgo and the push of the void, our galaxy's path becomes a complex dance through space-time, one influenced by both presence and absence. These combined motions, flows toward dense clusters and away from empty voids, define the large-scale velocity field of the universe. It's the cosmic equivalent of weather, vast currents of galaxies streaming through space, shaped by gravitational highs and lows. Where density increases, galaxies fall inward. Where it decreases, they flow outward. And in between, the cosmic web flexes and breathes as the universe expands. The velocity field isn't random. It carries the memory of how matter was distributed in the past. By measuring it, astronomers can reconstruct the shape and depth of nearby voids. When they do, the picture of our region of the universe becomes clear. The Milky Way lies on the edge of an enormous underdensity, flowing outward along with millions of other galaxies. In essence, we are part of the void's own exhalation. But these flows create complications for cosmology. When astronomers measure how fast the universe expands, they do so by looking at the redshift of distant galaxies, the stretching of light caused by space itself expanding. Yet peculiar velocities, these additional motions caused by gravity, also affect redshift. A galaxy moving away due to both cosmic expansion and local gravitational flow will appear to recede faster than it should. That's where the void plays its trick. From inside, every direction we look seems to show galaxies fleeing faster than expected. The outward flow from the void adds to the cosmic expansion, making the universe appear to expand faster locally than it does globally. This is one of the core ingredients in the Hubble tension, and one of the reasons the KBC Void matters so much. When cosmologists simulate a void like ours, 1 billion light-years in radius and about 20% underdense, they find it can add several hundred kilometers per second to the velocities of galaxies inside. That's enough to shift the measured Hubble constant by roughly the same amount as the observed discrepancy. The numbers fit, the physics works, the evidence aligns. But again, the problem moves one step deeper. How could such a massive void form in the first place? In the lambda CDM model, gravity pulls matter together over time, forming clusters and filaments, while the spaces between them gradually empty out. But simulations rarely produce voids as extreme as the KBC. To carve a region that large and that empty requires a chain of coincidences in the early universe, a sequence of density fluctuations that all happen to align in one region. The statistical odds are tiny, perhaps 1 in a billion. If the KBC void is real, something about our understanding of structure formation might be incomplete. Either the universe is more uneven than we think, or gravity behaves differently across cosmic distances. Both possibilities have profound consequences. Some theorists propose that gravity itself may weaken inside large voids. In a modification known as FR gravity, the curvature of space-time changes depending on the density of matter. In dense regions, gravity behaves like Einstein predicted. In emptier ones, the equations shift slightly, amplifying the difference in expansion between voids and filaments. This would make large voids more common, and possibly explain why we live in one. Others suggest the opposite, that gravity might have been stronger in the early universe, accelerating the evacuation of matter from underdense regions and creating voids more quickly. Each theory makes testable predictions about how galaxies move, how light bends, and how voids evolve over time. The way galaxies flow through space tells us which picture is right. If gravity behaves differently in emptiness, we'll see deviations in those flow patterns, subtle accelerations or decelerations that can't be explained by standard physics. Measuring these requires enormous precision, but new instruments are up to the task. The Nancy Grace Roman Space Telescope and the Euclid mission will soon map galaxy velocities across billions of light-years, providing the clearest picture yet of how gravity operates in the universe's vastest gaps. Meanwhile, our own motion remains one of the most striking confirmations that we live in an unusual environment. When astronomers measure the cosmic microwave background, they find a slight temperature difference, warmer in one direction, cooler in the opposite. That pattern reveals our motion relative to the background itself, 627 kilometers per second, or roughly 1.4 million miles per hour. That velocity isn't caused by cosmic expansion, it's our local motion through space, and its magnitude fits perfectly with what we'd expect for a galaxy sitting near the edge of a massive underdensity. We're moving faster than we should be if the universe were uniform. The void is real enough to push us. In a sense, our galaxy is surfing a gravitational wave, a slow, continuous acceleration driven by the imbalance of matter around us. We're not being pushed by emptiness itself, but pulled by what lies beyond it. The absence of mass on one side means more mass, and therefore more gravity on the other. The result is motion, not random but coherent, as if space itself were flowing. That motion subtly distorts our view of the cosmos. Because we are moving, galaxies in the direction of our travel appear slightly bluer, shifted towards shorter wavelengths, while those behind us appear redder. This dipole anisotropy in the CMB is a direct imprint of our journey through space. Astronomers correct for it when measuring cosmic expansion, but the correction assumes that our motion is small and local. Inside a void, it might not be. The entire region could be participating in a vast coordinated flow that biases every observation we make. The deeper we study the void, the more it feels like a mirror turned toward us. It reflects the limits of our understanding, showing how even the simplest forces, gravity and expansion, can weave illusions when viewed from the wrong vantage point. Inside a void, gravity doesn't reverse in any mystical sense. It still obeys the same equations. But those equations, stretched over cosmic emptiness, produce behavior that feels reversed, outflows instead of inflows, acceleration instead of collapse. It's a vivid reminder that physics isn't just about laws, it's about context. The same rules that build galaxies in dense clusters create expanding hollows in the voids between them. And we, perched on the edge of one of those hollows, experience both effects at once, drawn toward the dense walls of the cosmic web, yet carried outward by the expansion of the empty space around us. Our galaxy is caught in the cross-current between gravity and nothingness. In the end, that is what makes the KBC Void so fascinating. It's not just a hole in space, it's a place where the universe's most fundamental forces meet and seem to trade roles. Gravity, the eternal sculptor of structure, becomes the agent of expansion, and emptiness, far from being passive, becomes the engine of motion. The universe, it turns out, doesn't pull everything inward. Sometimes it lets go, and when it does, space itself begins to flow. For nearly a century, cosmology has been guided by a beautiful assumption that on the largest scales the universe is the same everywhere. This belief, known as the cosmological principle, tells us that the cosmos is homogeneous and isotropic, uniform in every direction, with no preferred place or perspective. It is the quiet foundation beneath modern physics, the reason we can describe the entire universe with a few elegant equations. It also carries a philosophical comfort. It says that we are not special, that the view from our corner of space is, in essence, the same as the view from any other. No centre, no edge, no privileged point of reference. But what if that symmetry isn't perfect? What if our region of space is different enough to matter? Recent observations suggest exactly that. The vast underdensity surrounding our galaxy, stretching billions of light years in every direction, appears to contain less matter than the cosmic average. It is a colossal hollow in the web of galaxies, and we seem to be living inside it. This discovery challenges the cosmological principle at its core, because if the large-scale universe is meant to look the same everywhere, then such a region should be extraordinarily rare. Yet here we are, surrounded by it. In standard cosmology, structure forms through small variations in the density of matter after the Big Bang. Gravity amplifies those differences. Dense regions collapse into clusters and filaments, while emptier ones expand into voids. On average, the contrasts balance out. By the time you look across hundreds of millions of light years, the universe should appear smooth. But our surroundings are not entirely smooth. The measurements show a deficit of matter extending over nearly 2 billion light years, far beyond what most models predict. It's not just a statistical blip, it's a genuine structure, and a surprisingly large one. To put that in perspective, the chance of such an underdensity forming randomly in the current cosmological framework is vanishingly small, a 1 in a billion coincidence. Yet somehow that coincidence defines our entire cosmic neighbourhood. Does this mean the cosmological principle is wrong? Not necessarily, but it may mean it's an approximation, not an absolute law. Perhaps the universe does approach uniformity only when viewed on scales larger than we can currently observe. Or perhaps it was never truly uniform to begin with, just remarkably balanced on average. In many ways, the assumption of perfect homogeneity has always been a simplification, a way to make an infinite, chaotic cosmos mathematically manageable. Without it, the equations that describe cosmic expansion, the Friedmann equations derived from Einstein's general relativity, become far more complex. If the universe is uneven, those equations no longer apply globally. They become local, contextual, tied to where we are. The idea that our location could influence our measurements feels unsettling. For decades, cosmology has relied on the principle that no observer is special, but if our region happens to be less dense than average, that principle weakens. We would not be the centre of the universe, but we would be in an unusual place within it. This is not the first time humanity has faced such a shift. The Copernican revolution began by removing Earth from the centre of creation. Later, astronomy displaced the Sun from the centre of the galaxy, and the galaxy from the centre of the universe. Each step reaffirmed a humbling idea, that our place is ordinary. Now, the discovery of this immense hollow in space hints at another refinement. We may not be central, but perhaps we're not entirely typical either. The universe could still be uniform on average, yet contain rare regions, deep voids and dense superclusters that make each location slightly unique. Some philosophers of science see no contradiction here. The cosmological principle doesn't require perfect uniformity, only statistical sameness, that every sufficiently large region contains roughly the same mix of matter and emptiness. Under that looser definition, our cosmic surroundings still fit. They may be unusual, but not impossible. Yet for others, the scale of the underdensity feels too extreme to ignore. If our position truly affects how we measure cosmic expansion and distance, then the assumption of universal sameness may have blinded us to subtle biases. Our data, after all, comes entirely from one vantage point, a single island of awareness within an ocean of space. In that sense, the principle of cosmic uniformity was never just about physics. It was about perspective, a declaration of humility in a universe too vast to fully sample. but humility must be balanced by observation. If the evidence shows that our local region is distinct, then honesty requires we acknowledge it. This leads to an even deeper question: why here? If our cosmic environment is exceptional, does that make our existence coincidental or somehow inevitable? Enter the anthropic principle, the idea that the universe must appear compatible with the existence of observers like us. We can only measure the cosmos from locations that permit life and structure. Perhaps slightly emptier regions are more conducive to stability, fewer collisions, less radiation, calmer environments for galaxies like ours to evolve quietly over billions of years. If that's true, then our position in a mild underdensity isn't surprising, it's self-selected. Out of all the possible places to observe the universe, we could only arise in those where conditions were gentle enough for life to endure. Still, the sheer scale of this vast hollow stretches that logic. A small underdensity might enhance habitability. A billion light-year void seems excessive. So perhaps the explanation is simpler. We live in a random fluctuation of the cosmic web, rare but real. A reminder that even a nearly uniform universe still has extremes. Future surveys will help clarify the picture. Instruments like Euclid and the Vera Rubin Observatory will map galaxies and dark matter to unprecedented distances, revealing whether our region is truly exceptional or merely one cell in a repeating cosmic pattern. If other vast hollows are found, the universe will remain statistically homogeneous, just more textured than we once thought. If not, then our position will stand as a profound anomaly, a quiet violation of the principle that once defined modern cosmology. Either way, the discovery reframes how we see ourselves. It reminds us that our entire understanding of the cosmos depends on where we stand within it. Imagine another civilization, far across the universe, living inside a dense filament instead of a cosmic hollow. Their sky would be crowded with galaxies, their measurements of expansion slightly slower, their estimate of the universe's age subtly different. Both views would be correct, locally. The difference would be perspective. That realization captures something essential about the modern era of cosmology. The universe may not be the same everywhere, but the laws that govern it are. The variation we see, in density and structure, in emptiness, is not a flaw, but a feature of those laws playing out across vast distances and deep time. Perhaps the cosmological principle, rather than being a strict rule, is more like an approximation of a deeper truth, that uniformity emerges from complexity, but never perfectly. The cosmos mirrors life in that way, balanced but never static, average but never identical. From our vantage point within this great underdense region, we still see the universe as a whole, expanding, evolving, breathtakingly coherent. The large-scale order remains intact. The principle still holds in spirit, even if the details demand revision. What this immense hollow really reveals is not a flaw in the universe's design, but the limits of our assumptions. It shows that the cosmos is both simpler and richer than the equations that describe it, uniform in its laws but varied in its expression. In the end, the idea that the universe looks the same everywhere may be less a statement of fact than a statement of faith, a faith in symmetry, balance, and simplicity. The growing evidence of vast cosmic structure doesn't destroy that faith, it matures it. It teaches us that perfection is not required for beauty, and that even an uneven universe can still be universal. We may inhabit an exceptional region, a quieter, emptier pocket of space, but from that vantage point we've glimpsed the grand pattern that binds everything together. Every great structure begins with a seed, even emptiness. The vast hollows that lace the universe, the immense stretches of nothing between galaxies, were born not from destruction, but from the faintest irregularities in the fabric of the early cosmos. To understand where the great voids come from, we have to return to the beginning. to a universe so young that time itself had barely started counting. In the first fraction of a second after the Big Bang, the universe was smaller than an atom and expanding faster than the speed of light. This period, known as inflation, stretched space exponentially, smoothing it into near-perfect uniformity. But inflation was not absolute. On the smallest scales, quantum fluctuations, tiny random variations in energy, rippled through the fabric of space. When inflation ended, those microscopic ripples were frozen in place, magnified to cosmic scales. What had been subatomic irregularities became faint over and under densities in the infant universe, the first imprints of structure. It's astonishing to realize how small those differences were. Some regions contained only one part in 100,000 more matter than others, yet gravity, ever patient, took those tiny differences and amplified them over billions of years. The slightly denser regions pulled in more matter, becoming the ancestors of galaxies and clusters. The slightly emptier ones lost matter to their surroundings, growing into the enormous voids we see today. In a sense, the universe's great hollows are the negative image of structure itself. They exist because gravity favoured their neighbours. We can still see the original pattern that seeded them, written in light. The cosmic microwave background, the oldest radiation in existence, is a snapshot of the universe when it was only 380,000 years old. To the naked eye, it looks uniform, a wash of soft microwave glow. But when viewed with precision instruments, it reveals a map of subtle temperature variations, red and blue speckles, each corresponding to regions slightly warmer or cooler, denser or emptier. Those colour differences, only a few millionths of a degree, mark the blueprint of everything that would follow. The bright patches became the filaments and clusters of the cosmic web. The dark patches grew into the voids between them. Over time, the universe transformed from a nearly featureless sea of hydrogen into a vast foam of structure, a process driven entirely by the slow competition between gravity and expansion. Matter fell into dense regions, while emptiness expanded where matter was scarce. By the time the first galaxies formed, the outlines of the modern cosmic web were already in place. Computer simulations now recreate this evolution in stunning detail. They start with those faint primordial fluctuations measured in the cosmic microwave background, then let gravity and time do the rest. Within billions of simulated years, threads of matter condense, knots of galaxies ignite, and between them, empty regions swell like air pockets in rising bread. The pattern that emerges, the cosmic web, matches what we observe in real galaxy surveys. But one detail keeps surprising researchers. The voids that form in simulations are usually smaller and shallower than some of those we see. Even when the models reproduce the web's general structure, they rarely generate hollows spanning billions of light years with such a deep lack of matter. That mismatch hints that something about the early universe, or about gravity itself, may still be missing from our equations. Some physicists propose that the initial quantum fluctuations were not purely random. Perhaps inflation imprinted subtle correlations across large scales, patterns that increase the likelihood of forming huge underdense regions. In other words, the seeds of emptiness might have been sown with more intent than chance alone would predict. Others suspect that our understanding of gravity could change at vast distances. Einstein's equations have passed every local test, from falling apples to orbiting stars, but they've never been directly tested across billions of light years. A small adjustment in how gravity operates on the larger scales could make large voids more common. And there's another possibility, simpler but profound. The universe might just be more variable than we assumed. The cosmological principle tells us that the cosmos is uniform when viewed from afar, but uniform might not mean identical. Perhaps our corner of space is simply one example of nature's full range. rare but not impossible. Whatever the cause, these immense regions of near-nothingness are not flaws in creation, they are part of its rhythm. They are the quiet half of the cosmic symphony, balancing the brilliance of galaxies with the silence of expansion. The process that built them is still at work today. As the universe expands, dense regions grow denser and empty regions grow emptier. Gravity and dark energy continue their slow tug-of-war. Gravity pulling matter inward, dark energy pushing space outward. In the hollows, dark energy wins. Expansion accelerates, stretching the voids faster than the cosmic average. The empty spaces are quite literally eating the universe, swelling, merging, consuming the walls between them. Billions of years from now, the great hollows will dominate. Filaments of galaxies will thin and isolate, leaving islands of matter adrift in an ever-deepening sea of darkness. The universe's structure will not vanish, but it will fade, its intricate web stretched too wide for its threads to hold. The fate of everything we know is written in that process. The same physics that gave rise to galaxies will one day erase their connections. The same quantum fluctuations that seeded the first stars also determined how those stars would end up alone. In a poetic sense, the voids are memory, the universe remembering the random ripples of its birth. They preserve in their scale and stillness the fingerprints of inflation itself, and yet there is beauty in their simplicity. If we could travel into one, away from all clusters and filaments, far from the bright heart of the cosmic web, we would find a sky nearly empty of galaxies. Stars would fade into isolation, and the faint glow of the cosmic microwave background would dominate the heavens. Time would seem to slow, space to stretch, light to thin. Gravity would be so weak that even the pull between galaxies would fade to near nothing. Such a place would feel alien, but also pure. There, the universe reveals its true nature, not a crowded stage of matter and fire, but a boundless fabric where structure is the exception and emptiness the rule. Indeed, more than 90% of the cosmos by volume is made of these vast underdense regions. Galaxies, stars, planets, and people exist in the remaining 10%, the cosmic residue of gravity's long labour. The universe is not a sea of galaxies with pockets of emptiness. It is an ocean of emptiness with scattered islands of light. And those islands, our galaxies, our clusters, our worlds, are what the voids made possible. Without the initial contrast between dense and empty, matter would never have gathered at all. The stars exist because somewhere else there was less. In that way, the origins of emptiness are the origins of everything. When we look out into space, we're not just seeing the aftermath of the Big Bang. We're seeing the consequence of quantum chance, the momentary flicker of energy that determined where matter would collect and where it would recede. Our existence is tied to that flicker. Every atom in our bodies was shaped by a statistical accident in the first trillionth of a second after time began. It's humbling to realize the same random fluctuations that built the galaxies also carved the deserts between them. We are products of both, the dense and the empty, the light and the void. The great hollows of space are not anomalies. They are reminders of the universe's true character, born from randomness, sculpted by gravity, and destined for expansion. They connect the quantum world of uncertainty with the cosmic world of structure. From the smallest vibrations in the fabric of space came the grandest architecture in existence. From nothingness came everything. And though we live among the galaxies, we're surrounded by that legacy of emptiness, not just in space, but in history, in origin, and in destiny. The universe began with tiny whispers of difference, and from those whispers, it built a chorus of light and silence that still plays everywhere across the stars. Every story has momentum, and the universe is no exception. The great hollows that thread through the cosmos are not static. They are growing, changing, shaping the fate of everything we see. Right now, across billions of light years, gravity and dark energy are engaged in a silent contest. Gravity tries to pull matter together, to knit galaxies into clusters and clusters into filaments. Dark energy, the mysterious pressure embedded in the fabric of space itself, pushes everything apart. For most of cosmic history, gravity was winning, but not anymore. Roughly 5 billion years ago, around the time the Sun and Earth were forming, the balance shifted. The universe's expansion, once slowing under gravity's pull, began to accelerate. That acceleration is driven by dark energy, and it is transforming the universe into something colder, quieter, and far emptier. In this new era, the voids are in charge. Regions where matter is thin feel less gravitational resistance. There is little to pull against the stretching of space, so expansion there runs ahead of the cosmic average. The hollows widen faster, swallowing up the boundaries that separate them. Galaxies at the edges drift outward like dust from a collapsing sand dune. In time, neighbouring voids merge, smaller pockets combining into larger basins of emptiness. The filaments between them thin like soap film, until only faint threads remain. The great web of galaxies is still there, but its structure is fading, dissolving into something more diffuse. The process is slow, cosmically slow, but relentless. Each billion years, the cosmic map becomes a little emptier. Every cluster grows more isolated. The deep hollows continue to expand, not just because of the stretching of space, but because matter itself keeps migrating away from them toward the denser regions at their boundaries. Our galaxy, the Milky Way, is part of that motion. It's being drawn outward, sliding along invisible contours in the gravitational landscape. We are already moving through space at more than 600,000 miles per hour, carried by the imbalance between nearby voids and distant clusters. To us, the motion is imperceptible, but across cosmic distances, it is destiny. If we could step outside of time and watch the universe in fast motion, the transformation would look almost biological. Filaments would pulse and fade. Voids would swell and merge. The bright structure of galaxies would retreat into scattered islands of light surrounded by black seas. That is the future written in the expansion of space. In perhaps 100 billion years, if dark energy remains constant, every major void will have grown far beyond its current boundaries. The distances between galaxies will have stretched so dramatically that even the light from neighbouring clusters will never reach us again. The observable universe will shrink not because it's contracting, but because light itself can no longer cross the ever-widening gulf. Future astronomers, if any exist, will look up and see only the fading glow of their own local galaxies. The cosmic web, once vast and intricate, will have disappeared beyond their horizon. To them, the universe will seem empty, eternal and static. The memory of expansion will vanish with the light. This is the cosmic isolation to come. In that distant epoch, each surviving cluster will become an island universe, drifting alone through a sea of darkness. The great hollows between them will grow so large that their boundaries lose meaning. Space will become almost perfectly smooth, not because it began that way, but because time and dark energy will have erased its structure. It's a paradoxical ending. The universe's complexity gives way to simplicity, not through order, but through emptiness. What began as a storm of matter and energy, structured by gravity into webs and walls, will end as an ocean of nothing, an equilibrium of expansion, where even gravity's influence fades into irrelevance. The voids, in a sense, are not just features of space, they are the engines of cosmic aging. Every time they grow, they drain the universe of contrast. They thin the filaments that give the cosmos its form. The more the voids expand, the less connected everything becomes. And yet, this progression is not decay. It's evolution. The universe is not dying, it is transforming. The same laws that gave birth to stars and galaxies now guide their disappearance. It's easy to think of voids as absence, as nothingness, but in truth, they are the purest expression of cosmic dynamics. They are space doing what space does best, expanding. While gravity fought to resist that expansion, it was only ever a temporary victory. The voids are the natural shape of an accelerating cosmos. Eventually, even the remnants of structure will succumb. Trillions of years from now, the last galaxies will exhaust their fuel. Stars will fade into embers, red dwarfs cooling to black dwarfs, neutron stars dissolving into silence. Black holes will dominate the night for a while, swallowing the last remnants of light. But even they will evaporate through Hawking radiation, leaving nothing behind but faint whispers of energy. At that stage, the universe will be almost entirely void. No stars, no galaxies, no filaments, just a thin mist of particles and the ever-growing fabric of dark energy. The great hollows we see today are the first outlines of that ultimate horizon. And yet, there's something profound in knowing this. Emptiness is not failure, it is fulfillment. The universe is not collapsing into chaos, it is expanding into balance. The same equations that describe the birth of galaxies also describe their fading. It's all one story, written in different chapters of time. From a certain perspective, the voids are not the end. They are the equilibrium the universe has been moving towards since the beginning. A balance between energy and geometry, between creation and stillness. But there's a more personal truth hidden in that cosmic future. When we gaze into the vast emptiness between galaxies, we are looking into our own future, not just the fate of space, but the fate of knowledge. Because someday, all traces of cosmic history will vanish from view. The evidence of the Big Bang, the faint glow of the cosmic microwave background, the redshift of distant galaxies, all of it will be gone, stretched beyond detectability. Civilizations born in that far future will have no record of where they came from. The universe will appear timeless and unchanging. Without clues to its expansion, they might conclude, as humans once did, that the cosmos is static and eternal. The truth will have dissolved into the void. In a sense, we are privileged to exist now, in the middle of the story, when the web is still visible, when the universe still speaks in light. We are witnessing the cosmos at its most articulate, just before the silence grows too vast to interpret. Our existence coincides with a fleeting balance, a time when matter, energy, and darkness coexist in comparable measure. This moment, the age of galaxies and observers, is temporary. The next will belong to emptiness. That's not a tragedy. It's the natural progression of a universe that began with contrast, with density and void, light and dark, creation and expansion, and now moves toward completion. Even in that distant epoch, the memory of structure will remain encoded in the subtle ripples of space-time, in the distribution of energy that once formed stars and clusters. The voids will not erase history. They will become it. In the farthest future, when the last photons wander through the great hollows, the universe will be quiet but not meaningless. It will still carry the imprint of everything that once existed. The glow of creation stretched thin, the echo of gravity's long retreat. The universe will not end with fire or collapse. It will end with distance, with light fading into invisibility, with silence expanding faster than sound. And somewhere, within that silence, will remain the same geometry that gave birth to all of this. A cosmic architecture built not from matter, but from possibility. Because that's what the voids really are. The places where the universe reveals what it's made of. Not stars, not galaxies, but space itself. The hollows between galaxies are not background. They are the stage. They are the canvas upon which existence paints its fleeting details. Without them, There would be no depth, no contrast, no meaning. So when we imagine the far future of the universe, a time when even the brightest lights have faded, we shouldn't see emptiness as an absence, but as a continuation. The void will outlast everything, because it is everything. The galaxies are temporary guests in its vast domain. One day, long after the last star has gone out, the universe will settle into stillness. The hollows will stretch until there are no boundaries left to define them. Expansion will continue indefinitely, but change will cease. The cosmos will become what it was always tending toward, not chaos but calm. And in that infinite quiet, the story that began with the first burst of light will come full circle. The universe, having built its structure from tiny fluctuations, will dissolve those structures back into the smoothness from which they came. The void, at last, will have completed its work. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow. Thank you.